Right, great. Let's continue then. We've been talking about L'Hopital's rule, which is something I think probably a lot of us are familiar with already. I thought that we should talk at least briefly about why it's true. It's kind of a magical rule, so I will just refresh our memory. The rule is when plugging in gives 0 over 0, then you can do this weird trick. Lim x goes to a, f of x over g of x is the same as lim x goes to a, f prime of x over g prime of x. All right, this is the formula for the L'Hopital's rule. When you plug into the function and you get 0 over 0, then the limit as x approaches a of f of x over g of x is the same as the limit of f prime of x over g prime of x. That's the L'Hopital's rule. Why is it true? Why? We don't need to go through a complicated proof of this. You can write down a real proof of this if you really want to. But I think actually you can sort of see why this is true on a picture. It's about that fraction over there versus this fraction involving the derivatives. Check it out. When I say plugging in gives 0 over 0, plugging in gives 0 over 0. Basically what that means is that, like, when you try to plug the number in, basically I'm talking about like doing f of a on the top and also doing g of a on the bottom. That's what I mean when I say plugging in gives you 0 over 0. So this means that f of a is 0 and also g of a is 0, right? That's what it means when I say plugging in gives 0 over 0. So that means actually we can think of this like on a picture. I don't really care where the y-axis is, but like if a is here, f of a is 0 and g of a is also 0. So these are two different functions, but they both go through that point. Their y values both equal 0. So maybe I will just draw something randomly here. There's one and there's another one, say. Let's say this is f and g. And they're both going through 0 right there. So that's what it means when I say if you try to plug it in, you get 0 over 0. It means both of the functions go through that point, all right? And now I have to try to explain why is it that the fraction, and what we're looking at in this, lim f of x over g of x going to a, right? That, what I'm talking about here is apparently like it's this height, which is f of x, divided by this height, which is g of x, all right? It's that ratio is the ratio of these heights. All right? And since it's this lim, really I'm talking about the ratio of those heights when it's like really close to A. All right? When this whole picture zooms really close into A, I'm talking about this ratio, the height of the f divided by the height of the g. And what does this have to do with the derivatives? Well, the derivative, remember, represents the slope of f and g. And if you recall, like the derivative is the slope of the tangent line of the f's and the g's, right? So check it out. If we zoom in, near A, this is the basic fact about differentiable functions. This is the whole idea behind the derivative. If you were to zoom in really close to A, now those pictures of f and g, they will just look like straight lines if you zoom in close enough. If f and g are differentiable, it means when you zoom in super duper close, they just look like straight lines, if you can imagine zooming way in, all right? They look like straight lines, and the straightness of them is determined by these slopes, right? So when I zoom way in near A, the F line looks like, it looks the same as it did before, but it looks straight now because I've zoomed in near A. And the G line also is similar, but it looks straight now, right? And now, would you believe me if I said, when you're really close to here, these ratios that we're talking about, they actually are the same as the ratios of the derivatives, because these are now straight lines. And the derivatives, like these heights here, are the slopes of these lines. And so the ratio of the actual heights is going to be the same as the ratio of the slopes of these lines. And that's the whole reason that the L'Hopital rule is true. So when we zoom in near A, if I had to say this sort of in words, the slopes, or the ratio of heights of F and G is the same as the ratio of these slopes. And what are those slopes? They are F prime and G prime, right? And so that's why f of x divided by g of x, I will say, is approximately equal to f prime of x divided by g prime of x for x near A. And in the limit as x approaches A, these are actually equal. And that's the whole point of the L'Hopital rule. It's because if you had to explain this to someone who doesn't already know what you're talking about, why it's true is because if I start with this fraction and zoom way in near the point, these heights, they just look like two slopes of two straight lines because I zoomed in, and their ratios will be the same. All right, this is why the L'Hopital rule is true. Any thoughts about that? This actually doesn't really have much to do with when you're actually, doing examples using L'Hopital's rule. You don't have to think all of this through. Did that checklist make it all the way around? Still working on it. All right, that's fine. Make a good choice. Okay, anyway, let's try just to do a bunch of examples. The L'Hopital rule is pretty straightforward to use. I just have a bunch of examples here. There are sort of easy ones, and there can be harder ones also, so we'll get there eventually. And there are also some slight variations. Anyway, let's try, this is a pretty straightforward one. Lim as x approaches 1, ln x divided by x minus 1. All right? I told some guy to fix the heat in here. I guess they didn't yet. Sorry. I'm working on it. I don't know if they're working on it. But okay, anyway, you should check, first of all, you need to, before you use L'Hopital's rule, you need to make sure that it's actually appropriate. That is to say, you get 0 over 0. So I'm going to start by trying to plug in the value. I get ln 1 divided by 1 minus 1. That is 0 on the bottom. And I hope everybody remembers the ln of 1 is also 0. So it really is 0 over 0, which means I can use L'Hopital's rule. So this is equal to, it's still a lim x goes to 0, but I'm going to take the derivative on the top and also the derivative on the bottom. So I get 1 over x here, divided by, I guess 1 is the derivative on the bottom. All right? It's a good idea to simplify that. Although I don't really know if it's necessary in this case, but that is just 1 over x, right? Divided by 1, doesn't matter. And then we should do this limit. And what's that limit? I plug in the 1 and I get 1. 1 over 1. The answer is 1. So here, we plug in 1 over 1. 1 is the answer. All right? This is how we do, this is a simple example of the L'Hopital rule. Sometimes when people do this, they like to write a little h right there. That was the step that I did, the L'Hopital's rule. All right. Any thoughts about that one? Everybody get the list? Seems like everybody got it. Thanks. All right, let's try. Okay, here's another one. This one is also fairly simple. Lim x goes to 0, cosine x minus 1 divided by x. All right. Again, you should begin by trying to plug the value in. If you get 0 over 0, that means you can do L'Hopital's rule. If you don't get 0 over 0, actually, you don't need to do L'Hopital's rule because you got the answer already. So this is the only The only purpose of it is when you get 0 over 0. So when I try to plug in here, I get cosine 0 minus 1 divided by 0. That's 0 on the bottom. Cosine of 0 is also 1. So this is 1 minus 1 over 0. So it is 0 over 0. All right. Then I should use the L'Hopital's rule. This is going to, I'm taking the derivative up top. Somebody say, what's the derivative on top? Sine x. And then on the bottom, the derivative of x is just 1. Sorry, I should write the lim again. You always have to do the lim of whatever you get there. All right? And now when I do this limit by plugging it in, we get sine 0 on the top, which is fine, over 1. So that's 0, right? Sine of 0 is 0. So the answer is 0. All right. All of these I would classify as easy ones. You just kind of plug the thing in, you get 0 over 0, then you take the derivatives, you plug it in, and you get a legitimate answer. All right? Okay, it can get a little fancier than that. Here's another one. How about lim x goes to 0, cosine x minus 1. This is very similar, but it's like that. It's got a root x on the bottom instead of just a x. All right. What's the difference? Well, again, we should start by trying to plug it in, but the same thing will happen again. So if we plug in, I get cosine 0 minus 1 divided by root 0, and this is still 0 over 0. It's a root 0 on the bottom, but that's still 0. So that's not really any different. All right, let's do the L'Hopital rule then. So this is cosine x becomes negative sine. It's the same on top, right? Negative sine x up top. Sorry, again, I forgot to write the lim. Should write the lim every time. And on the bottom, root x, as always, I think of that as x to the 1/2, and take the derivative. It's 1/2 x to the minus 1/2, like so. All right. Okay, now what are we going to do now? It should be, I don't know why I said it should be. It's a good idea to simplify here, right? You could just plug the number in. Is that what you're going to say?
Yeah.
Sorry, I didn't see the hand. Yeah, you could just try to plug the number in immediately, but it's a little confusing here. I'm going to simplify first. So I'm still got this lim out here. How can we rewrite this? I have 1/2 in the bottom, which is the same as 2 up top. 2, and then x to the negative 1/2 in the bottom. It's weird to have a negative exponent in the bottom. That's the same as x to the 1/2 up top. So actually there doesn't need to be a denominator at all here. You can say minus 2 sine of x times x to the 1/2, right? We had negative exponent in the denominator, which is the same as just having a normal exponent upstairs. All right? This isn't going to get any simpler than that, so we should try to take the limit by plugging the value in. So this is now negative 2 sine of 0 times 0 to the 1/2. 0 to the 1/2 is 0. Sine of 0 is 0. This is all 0. Sorry, that 0 is all 0. Because 0 to the 1/2 is 0 and sine of 0 is 0. All right? Any thoughts about that one? It's a good idea to simplify after doing the L'Hopital's rule. Sometimes.
Say you didn't simplify, then you get 0 over 0, and then if say you took the second derivative, would that be wrong? Would you get a different answer? Or do you think
this is a good question, and this is something that I was going to mention. What if I hadn't simplified, instead just immediately plug in again here? So what I've written so far, this is the correct answer, and actually what I'm about to write is not correct. So you may want to either don't write this down or put quotation marks around it or something. If you try to plug in again, you get minus sine 0 divided by 1/2 times 0 to the negative 1/2, which is 0 on top and 0 on the bottom. And then she says, let's do L'Hopital's rule again. Because I got 0 over 0 for a limit, I can just do L'Hopital's rule again. This is not a bad idea, but actually I've already done something wrong here. Can anybody see? Even what I've written so far, it has a mistake in it. This is a little sneaky, but important mistake. Okay, the mistake is not sine of 0 equals 0. That's true. It's something, it's on the bottom that is not quite
Well, isn't it
correct.
just wrong because the one above it is, like, you have to simplify? Isn't that why it's
I mean, to do it right, simplifying is a good idea. Although, in theory, you should be able to do it 2 different ways and get the same answer. There's a problem though.
Would it be undefined because 0 is the denominator?
Well, it's more like being at this step where I tried to plug it in. Yes, 0 is in the denominator, but then I'm going to go back and do L'Hopital's rule. So you could imagine doing a similar thing, but actually this is wrong. Yeah.
Because the 0 to the negative 1/2 denominator is a negative.
Yeah, that's the issue is right here. 0 to the minus 1/2. That by itself is not 0. You're used to saying 0 to any power is always 0, but it's not so. 0 to a negative power, like for example 0 to the minus 1 power, this is 1 divided by 0, and that's not 0, that's nothing, right? This is a does not exist, or you could say it's infinite or something like that. Anyway, so this right here is not 0 over 0. It's actually something like 0 over something which is infinite. That's the mistake with this strategy here. You don't even get 0 over 0 here, so you can't even do L'Hopital's rule again. So a bit sneaky.
So are you not even able to like move it up to the numerator and get rid of the negative?
No, I mean that's what I did here. Yeah. So like you could say, rather than saying this equals 0 over 0, you could, sorry, I'm getting crazy with the colors here. You could rewrite this like this, times 0 to the 1/2, move it up. But then, then that's the same as what I did anyway. So you would get 0 here, and that's just straight up the answer. You wouldn't go do L'Hopital's rule again. All right, simplify first. It matters. Okay, one more slightly tricky one. I don't know. Lim x goes to 2, x squared minus 3x plus 2 over x squared plus 2x plus 1. Let's try another, can you spot the error? Can you spot the error? This one, if I do L'Hopital's rule, I'm going to write this all in a different color because there will be an error in here. If I do the L'Hopital rule here, we get 2x minus 3 over 2x plus 2. And then try to plug it in. 4 minus 3 over 4 plus 2, 1/6. This actually is wrong. That's the step where I did the L'Hopital rule. Anybody see the problem here? Yeah?
So we actually just plug to.
Yeah, from the get-go, you notice in all the other ones I tried to plug it in and got 0 over 0. Here I just decided to go for it. But actually, you shouldn't just go for it, because here, this one, if you tried to plug it in, this is how you should begin such a problem. 2 squared minus 3 times 2 plus 2 over 2 squared plus 2 times 2 plus 1. That up top is 4 minus 6 plus 2 divided by 4 plus 1. That's 0 over 9, right? The true answer is 0. So the moral of the story here is you better make sure that you really do get 0 over 0 to begin with. Because if you don't get 0 over 0, not only like you're not supposed to do L'Hopital's rule in that case, but actually if you do the L'Hopital rule, it's going to give you the wrong answer. So don't do any of this stuff unless you are really sure that plugging in gives you 0 over 0. So the moral here is only do the L hop if we get 0 over 0, right? Otherwise, it will actually give you wrong answers. Don't even try it. How can it give you wrong answers? Well, it's because, like, remember this picture I drew at the beginning with the various slopes. If one of these things really isn't 0, like if that would mean one of these lines is not actually going through this point, but it's like up here somewhere, then when you zoom in, like everything is totally different. And none of this argument about the ratios, none of that is accurate anymore. And so you're not going to get the right answer. It only works when you get 0 over 0 from the beginning. All right. I can use this fact to trick calculus students by throwing in some where you don't actually have to use L'Hopital's rule. Although in our class, you know, this is going to be like number 9, I think it's number 10 on the test, is the L'Hopital rule section. If I'm just giving you one, I'm unlikely to make it one where you don't use L'Hopital's rule. But maybe if I gave you like 3 or 4 of these, I might throw in one where you don't actually have to use it. So look out for that. All right? All right, I got 2 more slightly harder ones. They don't really get all that hard, but they can be slightly more, I would say all the ones I've said so far have been kind of easy ones. Ones that can be slightly more involved. How about on the same theme as before, cosine x minus 1 over x cubed, all right? We did this one before without the cube, and we also did it with a square root down there. Anyway, you should start by plugging in cosine 0 minus 1 over 0 cubed. This really is 0 over 0, so I'm going to do the L'Hopital rule, and taking the derivative up top, cosine is negative sine, and on the bottom, 3x squared, all right? It's a good idea to simplify if you can, although nothing really sticks out to me here as wanting to be simplified, so I'm going to try to plug the value in again. Minus sine of 0 divided by 3 times 0 squared. That is 0 over 0. And now we can fulfill the dream that I think some of you have been holding on to all day. Let's do the L'Hopital rule again. You can do it again if you get 0 over 0. You should be a little concerned. Am I just going to keep doing it forever? Probably not. But you are allowed to do it again if you want to. Don't stop till you get enough. Squeeze gats till your eclipse is empty, as Biggie said. All right? So we're going to do the derivative on the top and on the bottom again. As long as you get 0 over 0, you can do the L'Hopital rule, and sometimes you have to do it more than once. So I have negative sine x up top becomes negative cosine x, and on the bottom, 3x squared becomes 6x, like so. All right. And you want to do it again? I don't know. You should always plug in first to see if you really need to do it again. I'm going to plug in and get minus cosine 0 divided by 6 times 0. That's negative 1 over 0. What does this mean? Actually, you should not do L'Hopital's rule again because it's not 0 over 0. What does it mean?
Like undefined.
Yeah, that means the limit does not exist. So you could say this in a few different ways, but I will just write, I'm usually going to write DNE, meaning the limit does not exist. You could say the limit is undefined if you prefer. You could say the limit equals infinity, although that's actually not true in this case. This limit, depending on which side of the 0 you come from, it could be positive infinity or negative infinity. And I don't really want to get into that, so I'm just going to say it does not exist. All right. So if you get 0 over 0, you can do L'Hopital's rule again. If you get some other number over 0, it means the limit does not exist, and you're done. You don't have to do any more than that. What if I get 0 over something else? That's just 0. Yeah, 0 divided by 3 or whatever. That's just the answer is 0. So, all right. So sometimes you got to do the L'Hopital's rule more than once. That was the moral of the story here. But make sure you stop when appropriate, right? You might be tempted to do it again from here, but actually that would get you the wrong answer. You would get 0 over 6 or something if you did it one more time, but you shouldn't. All right, one last one here of this same type. How about lim x goes to 0, tan x minus x over x cubed. All right. This is similar to the one we did up there, but it's a tan instead of a cosine. Anyway, we should start by trying to plug the numbers in first. And it's an x instead of a 1. It's a little different. Tan 0 minus 0 divided by 0 cubed. Anyone remember what's tan 0? Show me the fingers. You got fingers for that? If I ask for the fingers, it's either going to be this or fight the power. It's a 0. Tan of 0 is 0. I hope everybody remembers. So this is all 0, right? Well, it's 0 over 0. That means we can use L'Hopital's rule. So we go back, take the derivative. This is a weird derivative. Anybody happen to remember the derivative of tan? It's not all that weird.
1 over 1 plus x squared.
That's the derivative of arctan. Yeah, you're getting too fancy on me. This is an old-fashioned. Yeah, it's secant squared. I don't care if you remember this, but this is one of those trig formulas that maybe somebody told you to memorize. That's the derivative of tan, and then I had minus x, so that should be a minus 1, right? Over 3x squared. All right. Okay. You can try to simplify here, but I don't think that that's simplified, so we should just try to plug in. So I'm going to plug in and get secant. Sorry, I forgot to write my lim again. I left space there. I forgot to write it. Secant squared 0 minus 1 over 3 times 0 squared. That's 0 on the bottom. What is secant squared of 0? Anybody know? To me, secant is weird, but I always think of secant as 1 over cosine, right? So what is secant of 0 going to be? I see some fingers out there. The 1. Yeah, secant of 0 is 1 over cosine of 0, and cosine of 0 is 1. So if you wanted to write this out, this is the same as 1 over cosine 0 squared, right? That's the secant squared of 0. But cosine of 0 is 1. So that thing inside the parentheses is just a 1. So this is 1. 1 squared, right? Minus 1. That's 0 over 0. Okay, so we are going to do the L'Hopital rule again. All right. All right, this is kind of a pain. I have to do the derivative on the top and the bottom. The bottom is no problem. Derivative on the top, you have to figure out what is the derivative of secant squared. Maybe, would you mind if I do that as a little sidebar here? The derivative of secant squared x. That would be 2, you use the chain rule, right? So it's going to be the 2 comes down the front, and then secant x to the 1, right? And then I have to multiply times derivative of secant. Anybody happen to remember the derivative of secant? This is another obscure trig formula. Yeah? Yeah, it's secant x times tan x. My kid who's in high school now told me his teacher had some kind of joke about this. Anyone know what I'm... Yeah?
Mine was like, it was P, like P, S, S, T, and secant tangent. And secant was like secant tangent. And tangent was like secant squared.
I never heard of that.
Yeah.
Psst. All right. My kid told me about something like about sexy tan or something. I didn't really like that. What are they teaching my kids in schools these days? It's that woke education. They're sexualizing my kids. Anyway. It's like that, I guess, right? Just putting I have 2 secants there, so I'm going to put them together. All right? Okay, so this is the derivative on top. I also had minus 1, of course, here, but that's not going to matter when I take the derivative. So we get, this is my second L'Hopital rule application. 2 secant squared x tan x. And on the bottom, 6x. All right? We should try to plug in again. Actually, maybe because the numerator has no addition part here, I would rewrite this rather than using secants upstairs, put them as cosines downstairs. I just feel better about having cosines instead of secants. If you like secant, you can leave it where it is if you like, but I'm going to say, and can we cancel the 2 and the 6? Gives me a 3 on the bottom, right? So I'm going to write tan x over 3 cosine squared x times x, right? I moved the secants into the denominators and made it cosines because secant is 1 over cosine. And then simplify a little, the 2 and the 6 cancels and gives me 3 on the bottom. All right. Now let's do the L'Hopital rule again. So here, or no, we're not going to do it again necessarily. I'm going to try to plug in again. Sorry, I don't have space over there. I'm plugging the number in, tan 0 over 3 cosine squared 0 times 0. And that actually is 0 over 0. Tan 0 is 0, and on the bottom, cosine 0 is 1, but then I have this times 0. It's going to be 0 over 0. All right? So I'm going to do the L'Hopital rule one more time, hopefully the last time, but you never know with these things. So here, one more time, and this is going to be kind of nasty. Like, this is one of those cases in which you should wonder, am I just going to be doing this forever? Because it doesn't seem to be getting simpler, at least not obviously simpler. And in fact, it's going to look quite complicated after I do this step because I have to do the product rule on the bottom, which is going to be a pain. Let's see how it goes, though. The tan on top becomes a secant squared x. That's the derivative of tan. And on the bottom, I need the product rule because of that dot down there, the multiplication between cosine squared and x. So I'm going to do the product rule. The first part is 3 cosine squared x, like it is, times the derivative of the second part, which is a 1, and then plus the second part is x times the derivative of the other one. We're going to have to do the chain rule here because of the cosine squared. It's going to be 6 cosine x times negative sine x. All right. This one seems to be actually getting more complicated every time we do it, which I don't feel good about. This is a situation where I begin to worry that I'm just going to keep doing this and it will get increasingly more complicated. But actually, I wouldn't do that to you. This actually is going to end right here because when we plug the 0 in, actually, well, you can tell right away, actually, secant of 0 is 1 because secant is 1 over cosine. So we're not getting 0 on the top. That means definitely it ends here, right? It's not going to be 0 over 0 again. So this, when I try to plug in, is 0 up top and then a bunch of stuff down here. No, not 0. 1 up top. That's what I just said. And then a bunch of stuff down here. What is the stuff? 3 times 1, that's from the cosine squared, times 1, plus 0 times 6. The cosine is 1. The negative sign is 0. All of that on the bottom is 3, right? And that's my final answer. It was a lot of work for 1/3 is the true answer, all right? This I would describe as a hard one, although it's kind of just doing the same thing over and over again, but the derivatives are quite complicated to work them out. All right, any thoughts about that one? All right, I got some for you to try, but before that, one last variation, which can make these a little bit harder. So all of these that we've talked about have been one particular type, and I will say the L'Hopital rule is not only for 0 over 0, also works for things where you get infinity over infinity. And this one, I'm not going to try to draw the picture to justify. The geometry's a little weirder in this case because you're going to infinity. But I hope you'll take my word for it. L'Hopital's rule also works if when you try to plug the numbers in, you get infinity over infinity. And it works in exactly the same way. So here's an example like that. This, you get these infinities typically when the lim that you're talking about is going to infinity rather than a specific number. But something like this. Lim as x goes to infinity, e to the x over x. This you can use L'Hopital's rule in order to do. We start by, the plugging in step looks a little bit different, but by plugging in, I mean, what if you actually try to do x going to infinity on the top and also x going to infinity on the bottom? What you get is infinite over infinite, all right? This is because lim x goes to infinity of e to the x equals infinity, and lim x goes to infinity of x equals infinity, right? So I was just doing, you can say like, if you want to be casual about it, you could say, I'm plugging in the infinity on the top and on the bottom. Although, plugging in the infinity is not really something that you should not something you should say in public. It's like a red flag on Tinder or something. You don't plug in infinity. It's not a number. You don't plug it in. But really, what you mean is, I'm taking this limit on the top and also limit on the bottom, and I get infinity both times, all right? Anyway, if you get infinity over infinity, then you can use the L'Hopital rule in that situation also. So the L'Hopital's rule, and it works exactly the same way. You take the derivative on the top and also on the bottom. So you still put the lim here, but then I take the derivative on the top, I get the same thing again. I take the derivative on the bottom, the x becomes a 1. So that was the L'Hopital step. It looks like nothing happened on the top, but that's because I took the derivative on the top. And e to the x, you happen to get the same thing again. All right? But now when I plug the infinity in quotes, this equals, you could write this sort of informal step, it is infinity. This, I will maybe put that in quotes. Really, there is no such thing as e to the infinity, so you really shouldn't write something like e to the infinity, but what I mean when I say that is, if you let the exponent up here become infinite, then the whole thing becomes infinite, all right? That's how we do L'Hopital's rule involving infinities. All right, so the official sort of formalized statement of L'Hopital's rule, I'm going to write it as a theorem. It says, if my two functions f and g are differentiable, that means they have a derivative, and a is any number for infinity, and lim x goes to a f of x equals lim x goes to a g of x equals 0, or, this is kind of long-winded here, lim x goes to a f of x equals lim x goes to a g of x equals infinity. All I'm saying here is, when you take the functions, the original functions, and you try to plug in, you get 0 for both of them, or you get infinity for both of them. In either situation, then the conclusion is lim x goes to a f of x over g of x is lim x goes to a f prime of x over g prime of x, right? This is the formalized statement of the L'Hopital's rule. If when you try to take the limits, you get either 0 on the top and the bottom, or you get infinity on the top and the bottom, then you can do this. Change it into a limit of the derivatives. And hopefully that makes it simpler. Usually does make it simpler. All right. Last type of variation. There are still other indeterminate forms. These things which you use L'Hopital's rule for, they are called indeterminate forms. Like, for instance, 0 over 0 or infinity over infinity. It means when you try to plug something in and you get one of these, that actually does not give you any information about what the actual answer might be. The actual answer could be 0, or it could be does not exist, or it could be some specific number. There are others, though, also, something like 0 times infinity. I don't know if you ever wondered about this. This is like a playground conversation, or like a stoner conversation. Like, man, what is like 0 times infinity, man? Is that like 0 because anything times 0 is 0? Or is it like infinity because anything times infinity is infinite? Anybody know? Anyone had this stoner conversation before? I wasn't much of a stoner, but this is the kind of thing that I talked about on the playground from time to time. The true answer is that is an indeterminate form. You don't know what the answer will be. You should use the L'Hopital's rule with that. And similarly, also that, or here's another one, infinity minus infinity. Is that 0 because anything minus itself is 0, or is it still infinite because, of course, infinity minus anything doesn't really matter to infinity, right? Or maybe it's negative infinity. Like you kind of have to imagine which of these two infinities is going to win in the battle. It's probably not 0, right? They're not going to cancel, are they? I don't know. Anyway, again, the correct answer to this question is that is an indeterminate form. And if you really want to work this out, it will give you different answers in different situations, and you should use L'Hopital's rule. And the strategy here, the guidance that I have is simplify, or not really simplify, but I will say rearrange to force them into fractions, and then do L'Hopital's rule. All right. So if you ever do see something that looks like 0 times infinity, change it around so that instead of times, it's a division, and then it should be in a format where you can do the L'Hopital's rule. So I got just 2 examples of that type. Maybe 3, and then I have some for you to try. X times ln x, lim as x approaches 0. Can I throw in absolute values around the x there? Just because I don't want to worry. If I leave the absolute values out, there's issues plugging negative number into ln, but here it's fine. All right, x times ln absolute value of x. So we begin, as always, by trying to plug the value in. Of course, when I plug in x, this plugging in is just 0 times, well, I'll write it down, ln absolute value 0. What is ln of 0? It's not 1. ln of 1 is 0. ln of 0? Infinity? It's the short answer is you can't plug in 0 to ln. But since we're doing this business with the infinities or whatever, maybe you expected. If you recall, I hope everybody remembers the graph of ln looks like that, right? And if I put absolute values, it means you're allowing for negatives, but you'll get the same thing. So this is the graph of ln absolute value x, all right? And so I would say that ln of 0, at least when we're talking about limits here, is 0 times negative infinity, all right? And that is an indeterminate form. And I should be able to work this out using L'Hopital's rule. What I said here is you must rearrange to force them into fractions and then do the L'Hopital rule. Can anybody suggest how we would rearrange the original thing to force it to be a fraction rather than division? I want it to be division, not multiplication. Any idea? Yeah?
You just do x to the power of -1.
Yeah. So instead of x times ln x, I would write this as, I'm not doing the L'Hopital yet, I'm just rearranging. I think this is what she suggested. Like that. X up top is the same as x to the -1 in the bottom. Ordinarily, you would never do this because it doesn't make it simpler, but at least now it looks like a fraction, and when I try to plug this value into the fraction, I get minus infinity and infinity on the bottom, right? That's because plugging in 0 to the -1. Really, this is something like plus or minus infinity, but it doesn't matter. I'm getting infinite on the top and also on the bottom. And so this is the classic scenario in which you can use L'Hopital's rule. So we're going to do the L'Hopital rule now. This is the L'Hopital rule step. We still have x going to 0. Up top, ln absolute value x, the derivative of that is 1 over x. And on the bottom, the derivative of x to the -1, you do the thing with the powers. I go minus x to the -2. Right? Any suggestion what to do next? Yeah?
Put the x to the -2 up top.
Yeah, maybe simplify this. I have a negative exponent in the bottom, which I usually don't like. So I'm not doing the limit now, just rearranging things. How about put the x which is on the bottom up to the top, and the one which is on the top can go to the bottom, right? Because the bottom is a 1 over x. So I think when it's all said and done, I have a minus sign, but it's really that, right? We had 2 x's on the bottom, and then an x on the top, which was actually on the bottom. So it's like that. And then, of course, we can cancel one of those. Lim x goes to 0, minus 1 over x. And what's that limit? This limit does not exist. If you plug the 0 in, you get 1 over 0, which is a dne. So this limit is like a, well, it's like negative infinity, but I'm just going to say the limit does not exist, because this is a 1 over 0 now. Right? Yes?
Can you explain how you put x squared over x to the left?
This is bogus. Sorry, because I did it wrong. It should be just x here. This is not the right answer. Sorry about that. She was politely saying you did it wrong. It's true. Is that right? All right. You don't have to admit it. Yeah, it should have been that. Sorry, I simplified incorrectly. Now we plug the 0, even better. The answer is just 0. Right? All right. So we had to force it to look like a fraction. That was the point of this example. Let's do another one. Here is one which has, this will be our last one that I'm going to do, and then I got some for you all to try. All right, tan x minus secant x. This is the limit as x goes to pi over 2 from the left. That's what that stray little thing there. This is a little minus sign here. The limit from the left as x approaches pi over 2. Tan x minus secant x. All right. This one is weird. It might be helpful to draw a graph of these two things to know what happens when you plug in tan of pi over 2, because tan of pi over 2 actually is not defined. The graph of tan, I hope everybody remembers, looks like this, where this is a pi over 2, and it has this kind of repeated vertical asymptotes, right? And secant of x, I hope that this looks familiar to everybody. I don't really expect anyone to know what the graph of secant of x looks like, but it's 1 over cosine, and cosine is 0 at pi over 2. Yeah, sorry, I'm confusing myself. Cosine is 0 at pi over 2, which means when you do secant, you get a vertical asymptote there. And if you work this out or graph it on a calculator, it looks like that. There's another asymptote over here, and it continues. This one has sort of a guy up here, and then a guy down here, and then it's like that. But this is the only part that we care about. Anyway, just by looking at the picture, what are these limits? You can see as you approach the asymptote from the left, tan goes up to infinity. And as you approach the asymptote from the left, secant also goes up to infinity. All right, so when I try to plug this business in, I get infinity minus infinity. And that is the classic indeterminate form situation. So at this point, I realize I'm going to use the L'Hopital rule, although it's not quite obvious how to get there.
You do sine x minus cosine x.
Mm-hmm. Yeah, so we have to force this to look like a fraction. And it doesn't look like a fraction at all as written. You have to kind of think about, how could I rewrite this? And I think the suggestion was, and I like this idea, so this is not the L'Hopital rule yet. I'm just simplifying this thing. Write tan as sine over cosine, and write secant as 1 over cosine. And then those you can actually subtract the fractions. They have a common denominator conveniently. So this actually is lim x goes to pi over 2 from the left. It is sine x minus 1 over cosine x. And now I feel actually quite good about doing L'Hopital's rule with that. If we try to plug in here, it's going to be sine of pi over 2, which is 1, over cosine pi over 2, which is 0. So this really is 1 minus 1 over 0, 0 over 0. So we can do the L'Hopital rule on that. So I'm going to do the L'Hopital's rule right here, right? And it's not that complicated to do the derivatives. So this one becomes, this is the L'Hopital rule step. Cosine x, sorry, you should write the lim again. Lim x goes to pi over 2 from the left. Cosine x over negative sine x. Right. And plugging these in, cosine of pi over 2 is 0. Sine of pi over 2 is 1. So the answer is 0. I suppose negative 1 on the bottom, but it doesn't matter. The answer is 0. All right. Any thoughts about that one? These are the end. That was a lot of examples that I did. I got some for you all to try that will require, some mixture, some admixture of these various techniques. See what you think. Feel free to chat with your friends about it. There you go. See what you think. There's 5 different ones here.
Yeah, so you would,
From here. answers. Okay. That's right. Yeah, 3. This is not. This is an answer. I'm not saying it's wrong. You get 0. There's some examples where we got good. I would rather do those. Because you get 0. Yeah. Okay here? This is not. I meant for that to be going to infinity. Yeah, sorry, that's a typo. It should, yeah, the last one, sorry about that. It's ambiguous on my paper. It should be this, sorry. This I had written x going to 0. It should be x going to infinity. It matters. Sorry about that.
Okay.
Yes. Yeah, it's not one. This is when you see infinity over infinity, that's what you should do. Then you get this. That plus 1 shows. But anyway, here, when you try to plug in, you will again get infinity over infinity. So it's, you can't keep doing it. Let's go on here. This is not a number. Your answer should either be some number or 1 over this is, you see 1 over here? Because it's like 1 divided by some superposition. 0, right? That's great. Doing good here? Then it looks like a 1 over infinity. Infinity squared. There's no such thing as infinity squared.
So you just break it down.
Yeah, but this isn't right. Okay. This up top is not right. Sine of, like, think about Isn't okay here? Looks good. Did you give up on this one?
Yeah.
This is this is a little weird the way that you did it. It's easier to say x.
Yeah.
What's going here? This is a difficult one, I guess.
Well, was this right? When I bring that square down to the bottom, make it a fraction.
That's a good idea.
Okay.
Yeah, right.
Okay. And then,
Is that any better?
So
How to go.
that one.
I think this is good.
Then does this just become you do the things to do the locals? This one doesn't actually.
think it's, right, yeah, you should figure out what exactly is it. Maybe simplify it, because you have those guys. So.
Like what?
How you doing? This looks good.
How would the like final answer be?
That is 0.
Oh, okay.
Because it's like 1 divided by something. Which is, getting around this one?
Yeah, I'm gonna stop there. I don't like where.
This is alright. I think it's a little easier to keep the sign up top and then say X, the minus 2 on the bottom.
Okay.
Although this, in theory, that should also work.
Yeah.
Can we talk about these? I know not everybody's finished them all. That's all right. So the first one there, people did fine with. This is a very, very straightforward. I would say the first one is an easy one. You should get, when you try to plug in, you get 0 over 0. And so I do the L'Hopital rule, and I get 2x. Still lim x goes to 2. 2x on the top and just 1 on the bottom. Plugging in the 2 gives me 2 times 2, which is 4. So, and I think I saw that pretty much everybody had that one. Cosine x over sine x minus 1. Again, when I plug in here, this gives me cosine of pi over 2, which is 0. Sine of pi over 2 minus 1, that's 0 over 1 minus 1. So this is 0 over 0. So we should do the L'Hopital rule, and we get minus sine x with the lim, and on the bottom, cosine x. And then plugging in here gives me negative 1 up top and a 0 on the bottom. I'm doing all right? And then what do you say about that? DNE is what I say, yeah. Or you could say it's undefined or the limit does not exist, something like that. Yeah. When 0 is on the bottom, the limit does not exist. All right. All right. The one here with the infinity. Sorry, this one you try to plug in. You're going to get infinite over infinite if you try to make the top and the bottom go to infinity. 3x squared will go to infinity, and on the bottom that stuff goes to infinity. So you do the L'Hopital rule 2 times in this case. The first time you get 6x over 2x plus 5. Still lim x going to infinity. And still at this point, the top and the bottom are both becoming infinite. And so I can do it again and get this time 6 over 2. And the answer is 3. I saw pretty much everybody worked that one out also. Yeah?
Can we do it the way, like, if it's to the same power, just do the ratio of coefficients?
Yeah, you probably learned some trick about, and this is sort of like a memorized rule, which I'm not big on memorizing rules, but actually this one comes up often enough. If you have a ratio of polynomials and the limit is going to infinity and the degree on top is bigger, then the limit does not exist. If the degree on the bottom is bigger, the limit is 0. And if the degrees are equal, then the answer is the ratio of the leading coefficients. If you remember all that, you can immediately say the answer is 3 over 1, which is correct. But yeah, if this was a question on a test or something and you just said that, that's fine with me. Although I'm trying to make you do L'Hopital's rule in these ones. All right, great. Okay, x times e to the minus x. This one, when you try to do the infinity here, the indeterminate form is of the type infinity times 0. E to the minus x, when you plug the infinity, looks like e to the negative infinity, which really means 1 over e to the infinity, which means like 1 over infinity, which is 0. So that's why the second part there, e to the minus x, is actually is a 0. So this, anyway, I want to write it as a fraction so that I can do L'Hopital's rule on it. And you could do this 2 different ways. I think the easiest way is like that. You just change the negative exponent into a fraction like that. And now if I try to plug in now, I get infinity on the top and on the bottom, so I can do the L'Hopital rule, and it becomes 1 up top, e to the x on the bottom. And plugging in here gives me like a 1 over infinity. You shouldn't write that as your answer. What does that mean as an answer? It means 0. Yeah, this means a constant divided by something which is going to infinity is 0. Maybe I'll put that in quotes. The actual answer is 0, right? 1 over infinity is not really something that civilized people write. I know what you mean if you write that. Okay, and then the last one. This is the hardest one in my opinion. Sine of 1 over x is a weird thing to discuss, but if you think about what happens when x is going to infinity here, this, just sort of writing informally speaking, the x squared part turns into something infinite, and then this becomes something like sine of 1 over infinity, right? I'm just trying to imagine what happens when you plug the infinity in, as they say. Like I just said before, 1 over infinity means 0. So this is actually like infinite on the front, and then times sine of 0. So this is, again, an indeterminate form of the type 0 times infinity, or infinity times 0, all right? This is a little tricky, although, you know, once you know what's up, it's not so difficult. Okay, so we should force this into a big fraction. And again, you can decide to either put the sign in the denominator or put the x squared into the denominator. I prefer putting the x squared into the denominator, although in theory you should get the same answer either way you do it. So lim x goes to infinity, I'm going to do it like this. Sine 1 over x divided by x to the minus 2. I shove the x squared into the bottom, which means I have to put a negative exponent on it. And now we're going to do the L'Hopital rule. Like right now, actually, if we try to plug in, this is a 0 over 0. Sine of 1 over x, because of what I said before, is sine of 0 when x becomes infinite, and that's 0. And then on the bottom, this is like infinity to the negative 2, which is the same as 1 over infinity to the 2, and that's 0, because 1 over infinity is 0. So 0 over 0. I do the L'Hopital. Anybody get this far? What'd you get on the top? I know some people got this far. Anybody got something? Yeah?
Cosine x to the negative 1 times negative x to the negative 2.
All right. So yeah, she wrote 1 over x as x to the minus 1, which is a good idea. That's a chain rule on the top. All right. And then on the bottom, it's just the power rule, negative 2x to the minus 3. All right. We have powers of x on the top and the bottom, so I would like to simplify the powers of x. It looks like, well, I confuse myself with lots of negative exponents, but if I take the one on the bottom and put it up top, it's a x cubed, and I take the one which used to be up top and put it on the bottom, it's a x squared. And then I also have a minus sign up here, which will cancel this minus sign down here, but I do have a 2 on the bottom, which doesn't cancel anything. I'll just write it as a 1/2 in the front. Something like that. And now we can cancel x's. It's just going to be 1 x up top. And actually, it's not a fraction anymore, so hopefully this will be over. I don't think I'm going to have to do the L'Hopital again. 1/2 out front, x cosine x to the negative 1. And what happens here when you plug the infinity? It looks something like, okay, I have a 1/2, and then the x becomes infinite, and then I have cosine of 1 over infinite, which is 0. All right. Is this another indeterminate form, infinity times 0? I think it's not, because cosine of 0 is 1. All right. So this is actually just straight up infinity times, a 1/2 or something like that. Anyway, I say the answer is basically infinity, but I don't want to say the answer is infinity. I will just say does not exist, or you could say it's undefined. This is not another indeterminate, though. It really is something infinite. All right, that was a hard one. Sometimes I like a hard one. Any questions about that one? All right. I think that'll do it for today. This is all I want to say about L'Hopital's rule. We'll go on to the next thing next time. Let me know.